So now that we've looked at a whole bunch of completion stage methods, let's take a look at an application of these in a more comprehensive way. And we're going to apply them in the context of big fractions in order to show how you can chain together these dependent actions with completion stage methods to process the results of asynchronous operations and compose things together. And this example is the EX8 folder, as we've seen before. So if you look in the EX8 folder, you'll find there's a whole bunch of things in there. This is one of them. It's a program called test fraction multiplications 1, which sort of implies there's more than one. There's several variants. We're just going to look at this one, though. This particular program is going to generate a bounded number, in other words, up to S max fractions, of large, random, and unreduced big fractions. So we're going to generate these things, and we're going to use the stream generate method, and this will keep generating ad nauseum, but we put a limit on that. And what you do is you give a supplier lambda that gets called over and over and over again. And here's what the supplier lambda does. It's called make big fraction, and it's a factor method that makes a large random big fraction. So we pass in random number generator and a flag to see whether or not something should be reduced or not. The particular big fraction we generate is absolutely mammoth. You can see it's a number that's distributed uniformly over the range 0 to 2 to the 150,000ths minus 1, or plus 1, no, minus 1. That's a pretty big number. And then we go ahead and that's the numerator. And then we create a denominator that takes the numerator and divides it with a random number from 1 to 10. So these are big, big fractions. And then we go ahead and take the numerator and denominator, which are big integers, and turn them into a big fraction. And the reduced flag indicates whether to reduce or not. This particular example does not reduce because we want to reduce them concurrently, because reducing such a big fraction is going to take a while to perform. So we then take that stream of large, random, big fractions, and we're going to map them to a lambda function called reduce and multiply fraction. So every one of those big, the randomly large big fractions that are unreduced will be reduced and multiplied by the map operation calling this function. And here's what this function looks like. You can see it's a function that's going to end up taking a big fraction in, and it's going to return a completable future to a big fraction. And the way this works, because it's a completable future discussion, is it calls supply async. Supply async is the factor method we've talked about before. And you can see what it's going to do is it's going to call the big fraction reduce method to reduce the unreduced big fraction. And that will take a while because it's a big, as you saw, the numerator and denominator are rather large. And supply async, as I'm sure you recall, returns a completable future. When that completable future finishes, this action is then performed. So we're going to do then compose. We'll talk more about then compose in a second to remind you. Then compose is going to asynchronously take the reduced fraction that we got back as a result of asynchronously reducing the fraction through the factory method supply async, and then it's going to take the reduced fraction, it's going to multiply it by some other big fraction, which is a constant. So it's going to asynchronously multiply that. And because that's also a large fraction and we've got a big reduced fraction potentially, that'll take a while to run as well. So this is why we're doing it asynchronously in the background. Recall that we use then compose for situations where we have long-running asynchronous operations that return completable futures, and we want to flatten them or denest them so that we don't end up with a completable future to a completable future to a big fraction. We end up just with a completable future to a big fraction. So one way to do that is to use then compose along with supply async. Another way to do this, which I think I would actually prefer for a situation like this because it's more concise and more to the point, is to use the then apply async method. And if you recall, then apply async will asynchronously perform this action, returning a completable future to it. And so you get kind of the best of both worlds. You get then compose and supply async in a single one-stop shopping method. So that way we can avoid having to call supply async again. It's just a little bit cleaner. This will also run in a background thread. So what we're going to get as the result of this map operation is a stream of completable futures to ongoing asynchronous operations that are reducing and multiplying big fractions. So we're going to now have a stream of completable futures to things that are running in the background. So what are we going to do then? What we're going to do then is we're going to go ahead and we're going to collect that stream, and we're going to stick it into a mutable result container that we create. And this creator, this collector, as we call it, we'll talk about in the next lesson, the next part of the lesson. And what this is going to do, this futures collector dot to future factory method returns a single future to a list of big fractions that by the time everything is done will have been reduced and multiplied. They will be finished. But at the moment, we're getting back a completable future to ongoing operations. So there'll be a whole pile of them. Let's say, for sake of argument, that we're doing 1,000 of these big fraction reductions and multiplications. So rather than having to wait, or rather than having to deal with 1,000 of these things, we'll have a single completable future that will complete when the 1,000 of the other things it's waiting for are all completed. So this is an example of a reactive approach. We're going to be able to have this one and only completable future react when all the other things it depends on finish. And not surprisingly, what does this is the all of operation. We'll talk about that in a second. That's one of those arbitrary arity methods we talked about before. It's really cool. So what we get back from collect is a single completable future, and then we will accept this action if and only if that whole thing completes successfully, or when and if, or when it completes successfully. Let's assume it all completes. So when it succeeds, then this action will be called. And what that does, as the name implies, is it'll sort and print the results. Okay, so any questions about the overall flow here? This is really cool. So we're making an arbitrary, we're making an arbitrary number of big fractions, which we limit to be a fixed number of big fractions. We then go ahead and reduce and multiply them in parallel, because we do supply async for all these things, so that will get them all running in the fork join pool. We then collect everything into a single completable future, and then when that is finished, that implies everything else is done, and then we go ahead and sort and print the result. So let's go take a look at sort and print. Sort and print list sorts and prints a list of reduced big fractions. So by this point, I guess they're actually reduced and multiplied big fractions. So by the time it gets to this point, everything's been finished. And what we do here is that clever little trick I talked about last time, where we use quicksort and merge sort, and we start them both up running in parallel, because what the heck, why not? We got lots of cores. Let's put them to work, right? Let's not sit there and be theoretical about it and do some kind of analysis. Let's just run them at the same time and see which one finishes first. And whichever one finishes first, that one will be the one whose results we'll use to print the result, the sorted and reduced and multiplied results. So everything will get printed out when we're done in a sorted order. Now, an interesting question arises. What thread is this call going to run in? And if it turns out that both of these actions finish before except either is called, then the thread that calls except either will be used to print the results. However, if they're still running when except either gets called, then it'll turn out to be the thread in which the previous stage ran in, which would probably be a thread in a background thread in the worker thread pool for the fork join pool. Doesn't really matter, it's just an interesting side note. Something else to note here is that except either does not cancel the second future after the first one completes. So the first future to complete, we're going to take its result and go ahead and print it. But there's still that other sort routine running in the background. When that one finishes, we just ignore its results. We don't accept either does not cancel that computation. And the reason for that is that that completable future may be in use for something else. It could be used for some other purpose. And so accept either doesn't want to take the responsibility for canceling it. Yes, Matt? Oh yeah. No. It'll get rid of them because it'll be unused. Nothing will reference it. Good question though. The question for, if you go back and listen to it, was if the second whoever finishes second, obviously the result will not be used. Will that leak memory? And the answer is no. The garbage collector will clean it up. Okay, so that was basically an overview of how to apply the completion stage methods. And I think you'll agree it's really, really, really cool.